Gravity is the first rule you ever learn, without being told it's a rule. It is the quiet pressure beneath your feet. The reason air stays close to Earth. The reason oceans don't drift into space. The reason the moon keeps returning, night after night, to the same familiar arc. We treat gravity like a force, because that is how it feels. A pull, a downward insistence, something that keeps you anchored to the world. But that picture is a shortcut, useful, practical, and incomplete. Because gravity, in its deepest description, is not an invisible tether reaching out from planets and stars. It is not a mysterious hand that grabs objects and drags them inward. Gravity is something stranger, a change in the geometry of reality itself. For a long time, humanity didn't have language for that idea. We had experience. We had falling apples, collapsing towers, orbiting planets. But the why remained blurry. Then, in the 17th century, a new kind of clarity arrived. Isaac Newton wrote down a set of equations that made gravity behave like a universal law. The same influence that drops a stone to the ground also shapes the path of the moon and the motion of planets around the sun. For the first time, Earth and sky were governed by the same mathematics. Newton's formulation was breathtakingly powerful. It could predict tides. It could calculate the motion of comets. It could describe the rhythm of planetary orbits with astonishing accuracy. It even allowed astronomers to discover unseen worlds by noticing small deviations in known ones, an invisible planet revealed by the way it disturbed the path of another. But even while Newton's laws worked, they carried a quiet discomfort. Gravity was unlike other forces. Electricity could repel or attract. Magnetism could be blocked or redirected. But gravity only attracted. And it did so with a weakness that felt almost absurd on human scales. Two people standing a meter apart do pull on each other gravitationally, but so faintly that the effect is swallowed by everything else in the universe. Thermal motion, vibrations, electromagnetic noise, the restlessness of atoms. Gravity dominates not because it is strong, but because it is patient. Because mass accumulates. Because on cosmic scales, small influences add up, and nothing cancels gravity out the way positive and negative electric charges can cancel electromagnetism. For more than 2 centuries, Newton's equations felt like gravity's final truth, till they weren't. There was one problem that refused to disappear: Mercury. Mercury's orbit shifts over time in a slow rotation of its elliptical path. Newton's laws predicted most of this motion, almost all of it, but not quite. A tiny extra amount remained unexplained, small enough to ignore in daily life, large enough to persist in precise measurements, and stubborn enough to survive every attempted patch. Astronomers searched for an unseen planet. They adjusted calculations. They blamed observational error. Nothing erased the discrepancy. It was a flaw so small it looked like noise, and it turned out to be a crack in the foundation. In the early 20th century, Albert Einstein approached gravity from a different direction. Not as a force, but as a question about what motion really is. What falling actually means. What happens if you remove everything except the experience of acceleration? His answer overturned the entire picture. Gravity is not a force acting through space. Gravity is what happens when space and time are not flat. Einstein revealed that space and time are not separate containers. They are fused into a single structure, spacetime, where every event is a coordinate, not just in where, but in when, and where motion through space is inseparable from motion through time. And spacetime is not rigid. It responds. Mass and energy do not merely exist inside spacetime. They shape it. They bend it. They change the geometry that everything else must move through. A planet does not orbit a star because it is being pulled like a ball on a string. It orbits because it is following the straightest possible path through a curved reality. That sentence sounds impossible until you realize something subtle. Straight is not the same as looks straight on a flat diagram. In curved geometry, the straightest path can arc. On Earth, the shortest route between distant cities follows a curve along the globe's surface. A map makes the path look bent. The planet makes it natural. In Einstein's universe, gravity is that same concept, but deeper. Objects move along geodesics, paths of least distance in spacetime itself. In a region where spacetime is curved by a massive body, those geodesics converge. They tilt inward. They guide motion without needing a pulling force. This reframes the most familiar experience of all: weight. If you were truly under the influence of gravity alone, you would not feel it. That seems backwards, but it's true. Astronauts orbiting Earth are not beyond gravity. The gravitational influence at their altitude is still strong. They feel weightless because nothing is pushing on them. They are in free fall, moving along their natural geodesic. Weight is not gravity tugging you downward. Weight is the ground stopping you from falling. The floor, the chair, the pavement beneath your shoes. These are electromagnetic structures resisting your body's natural motion through curved spacetime. The force you feel is the world pushing upward on you, not gravity pulling down. Free fall is the natural state. Standing still is the interruption. This is why the equivalence between gravity and acceleration is so profound. If you were sealed inside a falling elevator, you would float. And if you were sealed inside a rocket accelerating through deep space at the same rate as Earth's surface gravity, you would feel the same weight you feel now. Inside the box, the experiences are indistinguishable. The geometry of motion replaces the idea of gravitational force. Once you accept this, gravity becomes more than a local phenomenon. It becomes a universal architecture. Time itself changes near mass. The deeper you are in a gravitational well, the more slowly time passes relative to regions of weaker curvature. Not as a feeling, as a measurable fact. Clocks tick at different rates depending on altitude and gravity. And this is not theoretical. It is engineered into the systems we rely on. Even light is not exempt. Light follows geodesics, too. When space-time curves, the paths of photons curve with it. Massive objects bend light into arcs, rings, and mirrored images of distant galaxies. The universe becomes its own lens, revealing invisible mass, dark matter, by how it warps the shape of what lies behind it. And if you keep following this curvature to its extreme, you arrive at black holes. Not cosmic vacuums, not hungry mouths in space, but regions where space-time is curved so steeply that every possible path forward points inward. The event horizon is not a physical surface. It is a boundary in geometry, a line beyond which outward stops being a direction the future allows. Black holes are where general relativity becomes both triumphant and incomplete. The equations predict their existence, their behavior, their shadows in glowing gas. Yet at the center, the mathematics breaks into infinities, signs that our description has reached the edge of what it can say. And that edge is where modern physics still waits, because general relativity is extraordinary, but it is not the final word. It does not speak the language of quantum mechanics. It cannot fully describe the first instant of the universe, or the deepest interior of a black hole, without stepping into unknown territory. So gravity remains, even now, both understood and mysterious. It is geometry we can measure, and it is a doorway into a deeper theory we have not yet found. And that is the twist that changes everything. Gravity is not just the reason things fall. Gravity is the shape of reality. quietly sculpting everything from the motion of atoms to the structure of galaxies, from the ticking of clocks to the fate of the universe itself. Time behaves strangely once gravity is understood as geometry. At first, this sounds abstract, like a detail that matters only to equations and physicists. But time is not a background feature of the universe. It is an active participant, and gravity changes it in measurable, unavoidable ways. When spacetime curves, clocks do not agree. A clock closer to a massive object runs more slowly than one farther away, not because it is damaged, not because it feels slower, but because the structure of time itself is stretched by gravity. This effect is tiny near Earth, but it is real. Atomic clocks placed at different altitudes tick at different rates, even when separated by less than a meter. This is not speculation. It is measured, and it forces a reconsideration of what time actually is. In everyday life, we imagine time as universal, a single river flowing at the same rate everywhere. General relativity shatters that idea. There is no single cosmic clock. Time is local. Each object carries its own rhythm through spacetime, shaped by motion and gravity. Near massive objects, that rhythm slows. Near extremely massive objects, it nearly stops. This leads to one of the most counterintuitive consequences of gravity. The closer you are to something heavy, the more you slip into the future, relative to distant observers. If you lived your entire life deep within a strong gravitational field, you would age more slowly than someone far away. When compared, you would have experienced less time. Gravity is not just shaping motion, it is shaping duration. And nowhere does this become more dramatic than near black holes. As you approach the edge of a black hole, spacetime becomes increasingly distorted. From the perspective of someone far away, anything falling toward the event horizon appears to slow down. Signals stretch. Light reddens. Time seems to freeze. But this is a matter of perspective. From the point of view of the falling object, nothing special happens at the horizon. No wall. No sudden force. It crosses the boundary in finite time and continues inward. What changes is not the experience, but the geometry of causality itself. Inside the horizon, all possible futures point toward the center. Just as you cannot avoid tomorrow, you cannot avoid the singularity. This raises a question that gravity alone cannot answer. What happens to information? According to quantum mechanics, information is never destroyed. It can be scrambled, transformed, hidden, but not erased. According to classical general relativity, anything that crosses a black hole's horizon is lost to the outside universe forever. Both ideas cannot be correct. This contradiction is not philosophical. It is mathematical, and it reveals something profound. Our best theories disagree about reality at its deepest level. This is why gravity is not finished. It works astonishingly well on large scales. It predicts planetary motion, gravitational waves, black hole shadows, and the expansion of the universe with extraordinary accuracy. But when gravity and quantum mechanics meet, at singularities, at the beginning of time, at the smallest conceivable scales, our understanding fractures. We are missing something fundamental. That missing piece is often called quantum gravity, but the name hides how radical the solution may be. It might require rethinking space itself, time itself, or the idea that space-time is fundamental at all. Some approaches suggest space-time is made of discrete units, like atoms of geometry. Others suggest it emerges from deeper principles, entanglement, information, or something not yet imagined. In these views, gravity is not a basic interaction, but a collective effect, like temperature emerging from the motion of molecules. If that is true, then gravity is not just geometry. It is a symptom, a visible shadow of deeper rules governing reality. And this brings gravity out of the realm of one force among many and places it at the center of existence. Gravity shapes the large-scale structure of the universe. It determines how galaxies form, how stars live and die, how matter clusters, and how time itself unfolds. Without gravity, the universe would be a thin fog of particles drifting endlessly apart. No stars, no planets, no chemistry complex enough for life. Gravity is the reason structure exists at all. Yet it is also the weakest interaction we know. This weakness is not accidental. Electromagnetism cancels itself out on large scales. Positive and negative charges balance. Gravity does not. Mass only adds. And over cosmic distances, that patience becomes dominance. Gravity builds slowly. But it builds everything, from the collapse of gas clouds into stars, to the merging of galaxies into clusters, to the vast filaments of matter stretching across the observable universe. Gravity is the architect. It amplifies tiny differences into grand structures. A slightly denser region pulls in more matter, becoming denser still. Over billions of years, this quiet feedback sculpts the cosmic web. Even the expansion of the universe is governed by gravity, or by something that behaves like its opposite. The discovery that the universe's expansion is accelerating revealed another mystery. Something is pushing space-time apart. Something that overwhelms gravity on the largest scales. We call it dark energy, but the name explains nothing. It simply labels our ignorance. Gravity pulls inward. Dark energy pushes outward. And the balance between them determines the fate of everything. Will the universe expand forever? Will it thin into darkness? Will it tear itself apart? Or will gravity eventually regain control in ways we do not yet understand? The answers depend on physics we have not finished discovering. And that is the final truth gravity teaches us. Reality is not a fixed script we are slowly uncovering. It is a layered structure, where each level of understanding reveals deeper questions beneath it. Gravity once seemed simple. Things fall. Then it became a force. Then it became geometry. And now it appears to be a clue, pointing toward a deeper description of the universe still waiting to be written. Gravity does not stop at stars, planets, or even galaxies. Its influence extends far beyond anything we can see directly, shaping structures so vast that light itself struggles to describe them. To understand gravity fully, you have to stop thinking locally and start thinking cosmically. On the largest scales, the universe is not random. Galaxies are not sprinkled evenly through space. They gather. They cluster. They trace immense filaments that stretch hundreds of millions of light years, weaving a structure known as the cosmic web. Between these filaments lie enormous voids, regions so empty that a galaxy could travel for billions of years without encountering another. This pattern did not exist at the beginning. In the early universe, matter was distributed almost uniformly. Almost. Tiny fluctuations, differences in density smaller than 1 part in 100,000, were present in the hot plasma shortly after the Big Bang. These differences were minuscule, but gravity does not require large imbalances. It requires time. Where matter was slightly denser, gravity was slightly stronger. Those regions pulled in more matter, becoming denser still. Less dense regions lost matter and became emptier. Over billions of years, gravity amplified microscopic irregularities into the vast architecture of the universe we observe today. Every galaxy, every cluster, every filament is the frozen memory of gravity at work over cosmic time. But most of the gravity shaping this structure does not come from ordinary matter. It comes from something we cannot see. When astronomers measure how fast stars orbit within galaxies, The results are impossible to explain using visible matter alone. Stars far from galactic centers move too quickly. According to gravity as we understand it, they should fly away. They do not. Something invisible is holding them together. This unseen mass does not emit light. It does not absorb light. It does not reflect light. It interacts almost exclusively through gravity. We call it dark matter. Dark matter outweighs ordinary matter by roughly 5 to 1. Without it, galaxies could not form the way they do. The cosmic web would unravel. The universe would look profoundly different. Gravity, once again, reveals both its power and our ignorance. We know dark matter is there because space-time curves where visible matter alone cannot account for the curvature. We map it through gravitational lensing by watching how it bends light from distant galaxies. We infer it through the motion of stars and gas, but we do not know what it is made of. Gravity tells us it exists, nothing else speaks. And beyond dark matter lies an even deeper mystery: dark energy. On the largest scales, gravity should be slowing the universe's expansion. Every galaxy's mass contributes to an inward pull. For billions of years after the Big Bang, that is exactly what happened. Expansion decelerated. Then, something changed. About 5 billion years ago, the expansion began accelerating. Space itself started stretching faster and faster, as if driven by an energy intrinsic to the vacuum. This acceleration is not subtle. It dominates the fate of the cosmos. Dark energy makes up nearly 70% of the universe's total energy content. Ordinary matter, everything we can see, touch, and measure directly, accounts for only about 5%. 95% of the universe is governed by components we do not understand. Gravity reveals their presence, but not their nature. This leads to a humbling realization. Our most successful theory of gravity explains how the universe behaves, but not what most of it is. And yet, gravity remains the thread tying everything together. From the smallest scales we can probe to the largest structures that exist, gravity provides continuity. It links the motion of falling objects to the expansion of space-time itself. It connects black holes to the birth of galaxies. It governs not only where things go, but how time flows as they go there. Even the origin of the universe is inseparable from gravity. When cosmologists trace the expansion backward, they find a universe that was once denser, hotter, and smaller. Eventually, all distances shrink towards zero. Curvature grows without bound. Time itself loses meaning. The Big Bang is not just a beginning of matter. It is a beginning of space-time. General relativity predicts this boundary, but it cannot describe it. At that first moment, gravity becomes infinite, and the theory collapses under its own success. Once again, gravity points beyond itself. It tells us where our knowledge ends. This pattern repeats throughout physics. Gravity works beautifully until it doesn't. It predicts black holes, but not what happens inside them. It predicts cosmic expansion, but not why it accelerates. It shapes space-time, but resists quantization. Everywhere gravity succeeds, it also exposes a deeper layer we have not yet reached. And that may be its most important role. Gravity is not just a law. It is a guide. It leads us to the edges of understanding and forces us to confront the limits of our concepts. Space, time, force, energy, information. All of them bend under gravity's influence, both mathematically and philosophically. When you look at the universe through gravity, you stop seeing isolated objects. You start seeing relationships. Motion is no longer something that happens in space and time. It is something that happens because of space and time. You are not separate from this structure. Right now, you are moving through space-time at the speed of time itself. You are following a geodesic shaped by Earth, by the Sun, by the galaxy, by the distribution of mass and energy across the observable universe. Your body is resisting that motion only because electromagnetic forces hold you up. Remove those forces, and you would fall. Not because something pulls you, but because that is the shape of reality beneath your feet. This is the quiet truth gravity reveals. The universe is not built on forces pushing and pulling across empty space. It is built on geometry, on relationships, on a fabric that responds to what exists within it. And we are embedded in that fabric. Gravity, when followed all the way down, does something unexpected. It stops being abstract. After galaxies, after black holes, after the expansion of the universe itself, gravity returns you to something intimate and unavoidable. Your own existence inside space-time. You are not observing gravity from the outside. You are inside it. Every moment of your life is a negotiation with curved space-time. Your heartbeat, your posture, the way blood flows through your veins, the way sound reaches your ears, all of it unfolds along paths shaped by gravity. Even your sense of stillness is an illusion. You are moving continuously through time, and that motion is inseparable from motion through space. From the perspective of space-time, you are never at rest. You are always falling. What we call standing still is simply a constant upward acceleration provided by the ground beneath you. The earth is pushing you away from your natural path. The chair resists your geodesic. The floor interrupts your fall. Gravity is not acting on you. You are acting against gravity. This inversion matters because it changes how we think about cause and effect. In a Newtonian world, forces explain motion. In Einstein's world, geometry explains motion, and forces explain resistance to geometry. This subtle shift has consequences far beyond physics. It means the universe is not a stage where events happen. The universe is an active participant in every event. Space and time are not passive containers. They respond, they stretch, they curve, they record the presence of matter and energy and feed that information back into motion. Every object writes itself into space-time, and space-time answers by shaping how everything else moves. This makes gravity deeply relational. Nothing exists in isolation. Your mass curves space-time, however slightly. The planet curves it far more. The sun dominates the geometry of the solar system. The galaxy shapes the motion of billions of stars. Clusters shape galaxies. The universe as a whole shapes the expansion of space-time itself. Everything influences everything else. Not instantly, not magically, but through the slow, finite propagation of curvature at the speed of light. Even now, space-time around you is responding to changes far away. Gravitational waves from distant black hole mergers are passing through your body as you read this. They stretch and squeeze space by amounts too small to notice, but they are real, ripples in reality itself, echoing events that happened billions of years ago. You are immersed in a dynamic universe. And yet, gravity also reminds us of our limits. There are places where our understanding simply stops. At the center of black holes, space-time becomes so distorted that the concept of after loses meaning. At the beginning of the universe, time itself appears to emerge from something we cannot yet describe. At the smallest scales, gravity refuses to fit into the quantum framework that governs everything else. This is not a failure. It is a boundary. Every great theory in physics eventually reaches one. Newton reached it. Einstein reached it. We are standing at the next edge now, looking into a region where space-time, matter, and information may be aspects of something deeper. Gravity brought us here. And gravity may be the clue that leads us forward. There is something quietly humbling about this. The same principle that makes a dropped object fall also governs the evolution of the universe. The same geometry that shapes galaxies shapes your future relative to someone standing a few meters above you. The same equations that predict black hole mergers also explain why your feet press against the ground. This is not coincidence, it is unity. Gravity is the thread that runs from the smallest human experience to the largest cosmic structure. It is the reason the universe has shape, history, and complexity. Without it, there would be no stars, no planets, no chemistry, no life capable of wondering why gravity exists at all. And still, after everything we've learned, gravity holds its secrets. We do not know what space-time is made of. We do not know why the universe accelerates. We do not know how gravity fits into the quantum world. We know only that gravity works, and that it points beyond itself. That is the final lesson. Understanding gravity does not make the universe feel smaller. It makes it feel deeper, more layered, more alive with unanswered questions. You are not living on a surface with a force pulling you down. You are moving through a curved reality that has been evolving for nearly 14 billion years. One moment, one geodesic, one quiet bend in space-time at a time. And that journey is not finished. Gravity also tells a story about the future. Not a prediction carved in stone, but a range of possibilities written into the geometry of space-time itself. The fate of everything, stars, galaxies, even time, depends on how gravity and expansion continue their quiet negotiation. Right now, the universe is growing larger. Not because galaxies are flying outward through space, but because space itself is stretching. Distances between unbound objects increase as the fabric of space-time expands. This expansion began with the Big Bang and has continued for nearly 14 billion years. For a long time, gravity tried to slow it down. Matter pulled inward. Galaxies attracted galaxies. Expansion decelerated. That seemed inevitable. A universe filled with mass should eventually feel its own weight. Then acceleration was discovered. Something is overpowering gravity on the largest scales. Something embedded in space itself. Dark energy does not clump. It does not dilute as space expands. As more space exists, more dark energy exists with it, driving expansion faster, not slower. This changes the ending. If acceleration continues indefinitely, the universe grows colder and lonelier. Galaxies outside our local group will slip beyond the cosmic horizon, their light stretched until it can no longer reach us. Future observers, trillions of years from now, may see only a single galaxy in an otherwise dark sky, unaware that a vast universe ever existed beyond it. Stars will exhaust their fuel. New stars will stop forming. White dwarfs will cool. Neutron stars will persist. Black holes will dominate the long night, slowly evaporating through quantum processes over timescales so long they defy intuition. Eventually, even black holes fade. What remains is thin radiation, elementary particles drifting through ever-expanding space. Time continues, but nothing meaningful happens. A universe near equilibrium, maximum entropy, heat death. This is not dramatic. It is quiet. And gravity, which once built everything, slowly relinquishes its grip. But this is only one possibility. If dark energy evolves, if gravity behaves differently at extreme scales, or if unknown physics intervenes, the ending could change. Expansion could slow. It could reverse. Space itself could tear. Or reality could transition into something we do not yet have language for. We do not know. And that uncertainty is not a weakness of science. It is honesty. Gravity gives us a framework, not a script. It explains how change happens, not why the universe chose these particular rules. It describes evolution, not intention. It shows us what follows from what exists, not what must ultimately be. And yet, within that framework, something remarkable has occurred. The universe has produced structures complex enough to ask questions about gravity itself. You, on a planet formed by gravitational collapse, orbiting a star held together by gravity, inside a galaxy bound by gravity, you have learned to read the curvature of spacetime, to measure it, to predict it, to detect ripples in it from events billions of light years away. Matter has become aware of the geometry it moves through. That may be one of the most extraordinary outcomes of gravity of all. Not stars, not black holes, but understanding. Gravity does not care if it is understood. It curves spacetime regardless. But the fact that understanding is possible, that equations written by minds like ours can describe the behavior of the universe across such scales, suggests something profound about reality. The universe is not only governed by laws. Those laws are accessible. This does not make us central. It makes us participants. Temporary, fragile, and small, but capable of insight that spans cosmic time. When you feel your weight, you are feeling resistance to geometry. When you see the moon, you are seeing free fall frozen into orbit. When you look at distant galaxies, you are seeing gravity at work across billions of years. And when you think about gravity, you are engaging with the deepest structure of the universe. Not a force, a shape, a relationship. A quiet curvature that connects everything to everything else. The universe continues to evolve. Gravity continues to write its story into space-time. And for a brief moment in that story, awareness exists, able to look outward and recognize the pattern beneath it all. That moment is now. And the geometry is still unfolding.